questions that we'll give. So just take note of it, right? It will be the solution which I'll send you all in the email, the PDF of these slides, alright? Alright, we'll do example 11 because it's not so simple. Example 11 is a case where, well, sometimes friction is just insufficient for doing its job. Alright, so remember the last lecture, we went through a couple of examples of how circular motion could be provided by different forces. For example, from gravitation or from friction. This could provide a centrifugal force. But roads are a kind of tricky because the road conditions vary from day to day. It can be raining and then suddenly you use a lot of friction that the car wheels would have required to move around a bend, which is nothing but circular motion, right? So sometimes it's possible to engineer a solution to this problem, and we'll take a look at how it works. So let's consider a car exiting the PIE to the DKE, those are expressways if you don't know. Alright, and it's exiting the curve at a particular speed, 50 kilometers per hour. That's a pretty safe speed. Okay, that's according to the road limits. Alright. For this question, we're going to ignore that friction exists. Okay, of course, although friction does, we want to see what other force can take over friction's place in providing the resultant force, the centrifugal force. Right? So we are given the radius of the curve that a car needs to bend, typically around this size or slightly smaller. Right? So a car on such a banked slope would be able to experience another force which contributes to the centrifugal force instead of friction. So that force can be the normal force. Right? Because the normal force must always be normal to a surface. If we have a car banked on the slope, this will be the two forces acting on the car. The normal force perpendicular to the slope and the weight of the car. Right? But they're no longer in the same line of action because the normal to the slope is no longer vertical. So what must happen is that this car must still be able to move around in circular motion. This is where the radius points towards. It's not down the slope because the circle isn't this way. The circle is horizontal, even if you're moving around a bend on a slope. Right? So if the circle's radius is in this direction, alright, we can tell that there's an unbalanced force. The normal force is actually unbalanced. Part of the normal force is horizontal component, that's going to be the resultant. And the vertical component of the normal force will just be used to balance the weight of the car. Right? So we'll do the same trick as we always do. We first find forces in the vertical direction and balance them. So the normal component, the component of the normal force, which is vertical, is n cosine theta, that must balance the weight. So left hand side n cos theta, right hand side the weight. That's our first equation. Okay, don't need to rush to copy, just understand first. Alright, you can always print out the lecture notes later on your own time. Okay, you have all the examples. I mean the lecture slide. Alright, that's the first example. That's the first equation that you can form. This is from resolving forces vertically and they are in equilibrium. Now, the car still needs to move in a horizontal circular motion. So we write down an equation for the horizontal circular motion. The net force must be the centrifugal force. So in this case, the x component of the normal force must be the resultant force, which is equal to mv squared over r. Alright, we're interested to find the banking angle, so we're going to get rid of the normal force first. So we'll take the first equation divided by the second one, the one from the vertical divided by the one from the horizontal, and get tangent theta. Right, then we inverse tangent to get 21.5 degrees. Alright, just take note that this 1000 over 3600 is to convert kilometers per hour into meters per second. That's all. Right, because in G we're actually using meters and seconds. So what the net effect of this is, if I'm able to keep a slope at 21.5 degrees, a car doesn't even need any friction in order to maintain circular motion by moving at 50 kilometers per hour for a radius of 50 meters. Right? It doesn't have to depend on friction at all. Of course, in reality, it's a combination of both of these factors, the friction, as well as the fact that we bank some of the roads. But not all roads are banked. Right? If your parent has ever fetched you to school, or you're going to catch from school, from the west side back to school at ECT, right? You'll notice that there's a big turn to come into VJC. Now that's circular motion because they're completing part of an arc of a circle. Right? And it's not banked at all, it's flat. So a very horrific accident happened last year. It was around, it was actually exactly on Labor Day itself. So on Labor Day holiday, early in the morning, there was a very bad accident there. It turns out it was my guild leader in World of Warcraft when I was in secondary school, JC, sorry. Yeah, so my guild leader died on that day. Yeah, I saw the famous and then saw his name, and then my friend told me, hey, that's our guild leader. You don't know what that is, right? Okay. Right. So it turns out, right, that he was moving at way too much a speed. So let's check. The speed is v, right? He's moving at a very, very large velocity. He wants to make a turn. Either he takes a very, very large radius, or he requires a very, very large frictional force to maintain the circular motion. So it turns out, right, that's because it's not a banked road. He has to rely entirely on friction. He couldn't make the turn in time. Right? Because he couldn't make a turn in time, it's two possibilities. If he's too slow, he would drift inward, which means he would bank the left side. If he's too fast, he would drift outwards, which means he would bank the other side, which is where a big tree was. And that same tree is still standing, but the car was flattened. So the first two people died. Yeah, and then just outside VJC journey. It was quite a terrible accident. Right? So that's what happens when you speed. So that's why we always consider the velocity, right, in our equations. And the velocity actually is a big factor. The velocity and the radius is somehow fixed in a ratio. And it's fixed in a ratio with our centripetal force. Right? So for a given car, to move in a particular radius, it can only move at a particular speed depending on how much force is exerted on it. If there's insufficient force and you try to move at that radius, or at that speed, the radius will either be larger or smaller than what you need it to be. They can't maintain that arc that you're trying to move in. Right, so a good example of engineering solutions to solve this problem where sometimes friction may not be enough is to create a bank with a particular angle. We can also actually calculate what the normal force on the car would be. And by just substituting theta into any one of the equations, so substitute theta into m cos theta equals to mg, and we get n equals to 10.5 kilonewtons. Right? So the normal force must now be larger than the weight, because it has to both provide the weight, to balance the weight, as well as some force to give the car centripetal acceleration. Okay, any questions? So not too difficult, right? Our problem solving strategy must sketch all the forces out, solve an equation in the y direction, which is usually balanced, then solve an equation in the x direction, which is unbalanced, and that will be equal to the centripetal force, and then solve accordingly. Alright, not bad. We've actually covered most of the normal centripetal questions, centripetal motion questions, circular motion questions, pardon me. Right? Now we're going to move on into the last chapter of circular motion, which is actually to say, since we're so familiar with circular motion already, we can now relax our requirement to have uniform circular motion or horizontal circular motion. We can either have vertical circular motion or non-uniform circular motion. By the word uniform, I actually mean that the speed is constant, that's all. So whenever I'm in non-uniform, it just means omega, v, f, and a might not be constant. It depends on the question. That's if I'm in non-uniform. Right? And sometimes when we solve a vertical circular motion question, we don't only use the circular motion equations, we can sometimes consider the energy. For example, if a pendulum is being swung in a vertical circle, alright, of course it will tend to speed up and slow down at different parts because it loses some of its KE and converts it to GPE. Right? So if you lose KE, you definitely have to slow down. So you tend to slow down on the way up and speed up on the way down. And if you speed up and slow down, you don't have uniform circular motion. That's non-uniform circular motion. Alright, so there are many physical examples. We'll go through a few now, but it tends to be roller coasters. So if you are a fan of roller coasters, today we are doing the physics of roller coasters. Hey, I don't like roller coasters. Let's get. Right. So let's consider example 13, a very special case of vertical circular motion, but it's still uniform. Somehow I make it uniform, alright? And then you can tell me why you think it's not realistic. So we'll identify 4 critical points in our vertical circular motion, A, B, C, D. Alright, so my object is moving with constant angular velocity. I know that because it's moving in a uniform circle. Uniformly speed is constant, V equals to R omega, R is constant, so omega has to be constant too. Right, so omega is constant as well. Now, I'm going to use my knowledge of uniform circular motion to find some interesting equations at these critical points, A, B, C, D. Right, so you're ready? Okay, so this should be under example 13. I want to find the forces acting on my object at point A for a pendulum being oscillated in a vertical circle, because I want to know what the tension in the string, and I want to know whether the tension in the string, right, will actually change between different points or not, or is it constant? We know the case for horizontal circular motion, the tension must be constant. Right, so let's look at this point. The 2 forces acting on the object are tension, which is upwards, and weight, which is downwards. So that's at point A, the lowest part of a vertical circle. Right? So in order to have been moving in a circle or to continue moving in a circle, tension must be larger than weight in order to have a centripetal force, right? So we can then identify the centripetal force as T minus mg, that gives me the net force. This equals to mr omega squared or mv squared over r, the centripetal force required to move in a circle. Alright, we can then make T the subject and write it down here. T equals to mr omega squared plus mg, that's all. Okay, if you identify this point, and you can understand this, actually you can understand the rest already, because it's just about balancing these 2 forces, T and mg. Anybody a bit confused? I can always re-explain this again. Okay. Alright, so because this object is at the lowest point of moving in a circle, we can identify what direction the tension must act. It's a string, so the tension must act upwards. But it has weight. The weight must act downwards. This is a vertical circle after all, don't forget. So not only that, the object must be moving in a circle. In order to move in a circle, it must have a net force. And that net force is the difference between T and mg. They can't be the same, because if they're the same, it will continue moving in a straight line here. Right? So T must be larger than mg. And by a certain amount, enough to produce mr omega squared, the centripetal force. Right, so if you understand this, let's take a look at B. Now, we still have the same 2 forces, but now they are not in the same line of action. Okay, let's consider B as an angle theta to the vertical. Okay, the tension and the weight now no longer lie in the same line of action. But I can still resolve my weight into a direction that is the same as the tension. I'll choose to do that, right, because I want to find out what is the net force in the center direction or the radial direction, right? If there's an arrow pointing along a radius, we call it the radial direction. So of course the radial component of the weight is mg cosine theta. The net force must still point towards the center. And tension minus mg cosine theta, that will be the net force that points towards the center. So that's the net force, but only considering the radial direction. Okay, so let's make T the subject and write it down. Two things to ask yourself now. Is the tension larger at A or is it larger at B? That's an easy question. Right? So you all can feel free to check with the person beside you if you all know the answer. Right? Is it A or B which has a larger tangent? Okay, and if it's B, or if it's B, then why is it B? If it's A, then why is it A? Right? Okay, so if you're done with that, the second question to think about is, why is this unrealistic? Right? From this particular vector diagram, you can tell that this motion is unrealistic. Right? What is it got to do with? Okay, go ahead and talk to each other about this one. Like, what makes the motion unrealistic? I'll give you all the answer in a bit, but y'all can discuss among yourselves or think about it first. Why is it unrealistic? The tension doesn't say that's okay. That's not unrealistic. Think a little bit more. Okay, so the first answer is easy, right? Why A is bigger than B? Because cosine theta is a number bigger than 1 or 0, and mg, the weight, is a constant. So this means that mg cosine theta is definitely smaller than mg. And because the object is moving in a uniform circle, that's one of the assumptions we started out with, mr omega square must be constant, because omega is a angular velocity. If you're moving in a constant speed, we must sweep out equal areas in equal times. Omega is a constant. The second question was a bit more difficult. What about this vector diagram makes the circular motion assumptions unrealistic? What makes this physical situation unrealistic? You can sound your friend now if you want. Right, just now discuss that. Your friend got the answer, you can point to what you said. Wow, it's really all so quiet. Nobody? David? David, you know the answer? Oh, then your friend can explain. Alright. What we have done here is we've resolved the weight into radial component, right? That's mg cosine theta. But weight now still has what we call a leftover component that we haven't considered. It's the other perpendicular direction. Or in other words, the weight has a tangential direction. And not only is it in a tangential direction, it's in a tangential direction opposite the direction of motion. Which means to say that by right, the weight is supposed to slow my object down, and that's what you expect. Right? As you climb higher and higher, you gain more and more GPE, you must lose KE. But my assumption of this question is that I'm moving in a uniform vertical circle. So that's where it's unrealistic. We have an unbalanced force here that is supposed to slow the object down. Right? In a tutorial, you'll encounter a question that's like this. It assumes that the speed is constant, but it's vertical circular motion. Right? So wait for people to discuss that with you. And you can think about it. Right, the last 2 points, the critical points of this vertical circular motion that we're going to discuss is actually pretty simple. So for point number C, okay, the weight is actually pointing in a perpendicular direction to the radius. It's now perpendicular, forming 90 degrees. So the weight can't affect the tension at all. The weight has no component in the radial direction. The tension is just mr omega squared. The weight doesn't come into the picture at all. Right, and right at the top, the weight and the tension are both in the same direction. Therefore, they both contribute to the centrifugal force. At D, the tension is mr omega squared minus mg. Alright? So because they were actually acting in the same direction, T plus mg equals to the centrifugal force. Once I make T the subject, T becomes mr omega squared minus mg. So we've got 4 different expressions of the tension at 4 different critical points in vertical circular motion. Because if A is bigger than B, as we have discussed earlier, A must be bigger than C and A must be bigger than D. So at point A, that's where the tension will become the largest. in a vertical circular motion, given our assumption that it's in a uniform vertical circular motion. Alright. So this is what animation of the magnitude of tension will look like in vertical circular motion. Right? The tension should increase as we go downwards and decrease as we go upwards. Right? So I got a live demo here for you. It should take a short time. So I'm sure you have seen cases where you can move objects in vertical circle. Your teacher will show you all interesting cases, but I can only demonstrate one not too life-threatening one here for you all. So I have a pail of water, and somehow or another, whoops. Alright, later I have to pop that up. Okay, so there's somehow or another, I'm able to swing this pail of water without spilling. Don't count that one, that was an accident. It knocked my shoe. So we're supposed to explain how come the water doesn't fall out of the pail, especially when it's right at the top of the circular motion, right? I'm going to a vertical circle. And maybe the front row people, you all go to like Universal Studios and all that, there's this water show, right? So you all can block your face. Right? Don't worry, it's pretty safe. So let's see if I can do it, alright? And try to notice what's required for me to do it. So there's water in this pail, okay? So this belt buckle is just some string. It's like a string. So I'm gonna attempt to swing this in a large vertical circle. Physics. Right? Physics. So none of the water came out on purpose, right? So somehow our circular motion should be able to, or when discussing circular motion, should be able to explain this. After all, the water is moving in a vertical circle. Right? What do you think I required to have at the very minimum for this to happen? Yeah, it's something to do with the speed, right? Because I was trying to swing it to give it some kind of minimum speed before I attempt to do the circle. So don't try this at home with a very slow speed. Right, let's take a look at the physics. We can consider the highest point, right? That's the point where we think the water should come out the most easiest, right? As the point which we should consider for our circular motion. Now, we identify all the forces acting on the body of water. Take note, we're not talking about the tail. The tail can move in circular motion just fine. We've done examples of this before, right? But the water is the one that seems to be a bit tricky. How come the water can not flow downwards but continue moving in a circle? Right, so all the forces acting on the water are labeled in this diagram. First, the water has a weight, that's mg. And if the water is in contact with any surface, it must have a normal force. So the water at the top of the bucket, bottom of the bucket, but now at the top, is in contact with the bottom of the bucket, which is now at the top. So that gives it a normal force. So we're going to write down the centripetal motion equations, circular motion equations for these two forces. Mg plus n to give me my centripetal force. That's all. Right. So I'm going to make this claim. The water will actually only remain in the pail, right? If the normal force is greater than 0. Right? Think about it. The only time the normal force on your body is 0 is when your leg is not in contact with the ground. So the same thing must be true for the water. As long as the water is in contact with the pail's bottom, there must be a normal force. Once that normal force goes to 0, the body of water is just riding below the pail surface. It's hovering right below as it completes its circular motion. Right at the top, it will be just nice, hanging below the pail but not touching. That would be what we call the critical point, right? In which the normal force goes to 0. So if the normal force is greater than or equal to 0, I can substitute n greater than or equal to 0. I find that my v becomes an inequality. It's an inequality related to the square root of r and g. And that's why you all claim that, hey, it was a speed in which I was looking out for a minimum. I require a minimum speed, and this is the minimum speed I require. Right? If I have any speed less than this speed, the water will start to fall in a circle smaller than the radius in which I want it to move. And that's considered the water spilling out of the pail. Right? Alright, so we have solved the water in the pail problem. Not bad, right? Now, you may think this is a trivial, trick that I can show you all in the lecture theatre, right? But it's actually quite applicable. Right? Fighter pilots and astronauts experience these problems when making tight turns or having large accelerations, which is when your brain doesn't receive sufficient oxygen, you tend to pass out. And the way the brain receives oxygen is the brain is a big pail of blood. Right? The brain is nothing but a big pail of blood. So when I'm swinging my pail, alright, when I'm swinging my pail, the water will tend to rush out of the pail as long as I'm not spinning it enough. Right? So by some kind of similar logic, when my plane is performing some kind of big turn, alright, there's a centrifugal acceleration on the entire person. Right? But the blood in the brain wants to remain in the brain, but because of the way it's accelerating, the blood tends to be drawn out of the brain. And when sufficient blood is drawn out of the brain loses the oxygen, you pass out. So that's called a very high G turn. So sometimes when we watch movies, like my favorite is Top Gun, right? They talk about the turn being too high in G. Too high in G, you don't want the blood to have too much, to flow too much out the head. Otherwise you'll pass out. So there are ways to mitigate this. You have to think about it, right? How would we mitigate something like this? Okay. But definitely one thing is training, getting used to having less blood in your head. Right. Couple more examples before we're done. So let's take a look at this scene. It's a pretty simple example. Okay. It's quite similar to the one we've done before. We have sort of something like a pendulum. It's a stone of mass 0.6 kg attached to a string, and then now we make it go in a 0.5 meter radius circle, vertical circle. We are expected to calculate the maximum speed of the stone and the maximum number of revolutions it can make per second, which is nothing but its angular velocity. We are still maintaining the special condition that is uniform, yeah? So, we have learned from previous cases, right, that the tension in the string will be the largest at the bottom. That's why that's the case we'll consider in this example. We'll consider the pendulum at the bottommost of its vertical circle, right, labeling all the forces acting on it. This is when I expect the tension to be the largest, hence the closest to breaking. Right, so the question asking for a maximum speed. And I know that's somehow related to the breaking tension of the string. Just like one of the examples we did earlier, but that was the horizontal circular motion. Right? So in the vertical circular motion, the tension we know can vary. So we have a couple of choices. We have to choose which point of the vertical circle we want to consider our forces. So from the previous example, we know that at the bottom of the circle, that's when tension is the largest. So let's consider that point. There are two forces acting on my pendulum board, the stone in this case, tension and weight. Right? So writing the circular motion equation, the tension minus the weight gives me the net force, and the net force must be the centrifugal force. So equals to mr omega squared. I'm choosing this version because I know I need to calculate omega later on. Alright, so I can write down the same version for velocity as well, because the question A asks us for maximum speed. So I'm able to identify that the maximum tension is associated with maximum speed. So I straight away label that as max mass. Alright, making V the subject and subbing in all the values that I need to get. This is the maximum speed. What happens when my speed exceeds this speed? Yeah, it will break. It will break because when this velocity is large, when this speed is large, sorry, the numerator becomes larger. So this Tmax must become larger. But Tmax is already the maximum tension. It can't deliver any more larger tension, so it will break. Okay, now to get omega from V is quite easy. Use V equals to R omega to get 1.4 revolutions per second. We did that in the first lecture, right? Convert omega into from radians into revolutions per second. So not too difficult question. So example 16 is a difficult one because now we're going to relax the requirement that the speed is constant. Okay, so this two diagram shows two different sections of a roller coaster. Alright, now one section of the roller coaster, the cart is above the track. Alright, that's like on top of the hump. Right, so there are a couple of kinds of roller coaster. One of them hangs on the inside of the cart, of the track, and the other hangs on the outside. So we consider this is like the human versus Taiwan or USS. Alright, so we consider this portion. Right? And consider all the forces acting on it. We're supposed to find what's the max speed of the car at this position. So it's a bit like the case of my tail and the case of the tail is the first case that we talked about with a normal force. But in this case, consider this arc, roller coaster arc, right, with a particular radius, with a cut of particular mass and speed. We label all the forces acting on it that we know of. So of course, first is its weight. And because it's resting on the track, it has a reaction force. So I'm going to make the same argument I did for the pail case. The only time when the water will leave the surface of the pail is when the normal force goes to zero. So the same thing here, if the cart were to lift off the track, that's the bad case that we don't want to happen, the normal force must go to zero. So let's write down our centripetal motion equation again. The weight minus the reaction force gives me centripetal force. So this is the same equation here. Now I'm going to suppose the car just hovers on top of the track as it makes its circle. Right? It just nice barely makes a circle. So at the top of the track, the reaction force goes to zero. So the car is actually really just gliding over the track at that point in time. So we set R1 equals to 0. This speed is the maximum speed in which we can travel this part of the circle. If you look at the equation on top, if the speed were to be larger, then we can't have any reaction force, right? Because the weight mg is the maximum value the left-hand side of the equation can possibly take. So the case in which we just leave off where r equals to 0 definitely must correspond to the case where we have the maximum speed. Okay, that's of course assuming the radius of the circle is a constant. So we sub into the equation the other values of the radius and g. We end up with 14 meters per second. So if the roller coaster car travels faster than that, it will lift off the surface. Yeah, it would fly. Precisely. So for this portion of the track, we're going to use the same argument as the tail in the water in the tail case, where the normal force goes to 0. But in this case, let's say the normal force goes to 0. It's a critical case in which the car just barely lifts off the track. So this is the critical case, same as the previous case. Right? Now, in question B, it's pretty similar to question K, but now the roles have reversed. The car is not at the bottom of its track. Right? And to answer the question that is in the lecture notes, what is the apparent weight the person feels when inside the car? Well, one has to understand what apparent weight means. Right? How do we feel our own weight? Well, now you're happily sitting on your chair, you feel your regular body weight. But if you were to leap off, say, the edge of a pool, before you hit the pool, right, you are what we call free fall. There's nothing supporting you for an instant. For the instant, you will feel weightless the moment you left the board. Right? No air resistance, you just pure gravitational force acting on you. But you don't actually feel your weight in that case. That's when you feel weightless, even though there's a net force gravity acting on you. So we can only feel our apparent weight when something presses us back in return, which is quite an ironic way to think about things. We think about our apparent weight depending on the upward force, the upward reaction force So in this question, we're supposed to calculate the apparent weight of the girl. So we first need to find the weight of the girl. That's quite easy. Mass times gravitational acceleration will give us 294 newtons. So that's the easy part. This scenario is the reverse of the scenario you will probably have in USS if you have taken the Jurassic Park ride. The Jurassic Park ride is a balloon ride, right? You sit on the river, it goes through some nice animation, robotic dinosaurs until you get to the top. And then you plunge. But for the instant, before you plunge, you will feel weightless. So that feeling is apparent weight equals to 0. Now in this case, right, I'm going to show you apparent weight would actually not go to 0. Right? In fact, I would like you to think about your intuition. Now, if you have sat roller coasters before, going down the arc of a roller coaster, will you feel heavier or feel lighter? Use your intuition, get an answer, and then we'll derive it and see if it agrees with our answer, our intuition or not. Okay, use your intuition. Right? Imagine being in a scenario. Don't use your physics yet, just use your imagination. Alright? Do you feel the feeling in which you are being compressed more? Or do you feel the feeling in which you feel lighter? Right? So that's the question. So we set up the question the same way we set up all the other circular motion questions. Write the radius down, write the velocities, the weight, and of course now that we're at the bottom of the track, the reaction force acts in opposite direction. It acts upwards. Right? So the centripetal force is nothing but the reaction force minus the weight now. Okay, that equation is now here. Right, R2 is the reaction force. That's the apparent weight, not mg anymore. Mg is the actual weight. The apparent weight you feel is the reaction force. So making R the subject and calculating R, we will get 582 newtons, and that's almost double of the original weight. So she must feel like she's heavier. So if you say lighter, right, we have bad intuitions. Right? This is the feeling, right, of being pressed down into your seat as you go underneath the arch. Right? Now, if you have said pirate ship before, right, you have very similar feelings. On the way down, you feel lighter. It feels like your heart is going to come out of your mouth. That feeling is the reduced apparent weight feeling. And the feeling of being crushed into your chest, right, which is when you feel when you go down into a very fast loop, right, going downwards into the loop, that's the feeling of increased apparent weight. So apparent weight is nothing more than the reaction force your body feels. It's quite ironic, right, because the reaction force are usually upward forces in these cases. So the reaction force is your apparent weight. You can't feel gravity by itself, you only just fall. Free fall, you feel weightless. Right? But that's not really being weightless because you really have a weight. Right? The only way in which you can feel your weight is when a reaction force acts upon you. And you feel that reaction force as well. And that's what you feel as your weight. Okay? So if you have not seen dynamics problems about lifts, that's another very good example of how to reduce or increase your apparent weight because of acceleration. It's just that in this case we're having circular motion. So of course the reaction force must be larger than the weight at the bottom of the circle. And then we feel as if the apparent weight is larger than our original weight. Alright, so that's the last vertical circular motion question we are going to be attempting. Right, there's just one more example. It's a difficult example to understand, but it's also a very realistic example because all of you cycle, right? Every single one of you. Right? And when you go around a bend, you go around the bend vertically straight, or do you have a tendency to lean your body towards the bend? Yeah, you all know that, right? See, this is an intuition. It's something you experience from real life, so therefore you know about it. Right? Today we're going to show that the physics agrees with what your body naturally does. Alright, and to a certain extent, if you have watched motorsports, which is when motorcycles do racing, you notice that the guys in the motorcycle almost have their knees touching the ground when they make big ups. big pass up. Right? So today the physics we're going to try to justify this. So we got a typical cyclist trying to make a turn of 5-meter radius, and he's moving at 7.5 meters per second. Must be a road bike. Alright, and the mass of the cyclist and the bicycle is 100 kilos. So we're supposed to find the centripetal force. That's easy. Right? Finding centripetal force, F is mv squared over r, v and r we know, and m we know. So we get a very, very simple value of 1.13 kilonewton. That's not the difficult part of the question. Alright, so I'm going to set up the problem here for you. We got a person on a bicycle. Okay, this is the center of the track, the radial direction. This is his weight. This is his normal force. So which force provides the centripetal force? It's not normal force, that is not pointing towards the center, right? What force could possibly point towards the center? That's right, it's friction. Because this is an unbanked surface, the only possible force that acts towards the center is friction at the wheels. Alright, so that's friction. So maybe we tilt our body because we are not in equilibrium. What do you think about that argument? We tilt our body because we're not in equilibrium. That's the problem. It's not right. We need to not be in equilibrium in order to move in a circle. Moving in circular motion is to not be the translational equilibrium in the first place. So it's okay for the cyclist to not have translational equilibrium. He needs to have translational, he needs to not have translational equilibrium in order to move in a circle. So it's okay that there's a net force acting on him. In fact, the net force will be friction, and that will be providing his centripetal force. So no issue. But then what's the problem? Can the cyclist not be in rotational equilibrium there? If I'm not in rotational equilibrium, what happens to me? Yeah, falling down, that's generally not good for cyclists, right? I don't want to be in rotational dynamics, right? So it's okay for me to not be in translational equilibrium. That will just affect the directions in which I'm moving my velocity or speeding up or slowing down. That's fine. I don't want to topple, and to topple means I don't have rotational equilibrium. So, is this cyclist in rotational equilibrium? Okay lah, huh? He falls down this way. I'll show you why he falls down this way with a diagram. Okay, the wheels will point inwards. Right, so sorry, I reversed the diagram direction. I don't know why I did that some years ago. Alright, so now the frictional force points towards the left. Okay, let's consider moments at the center of mass of the person. Right, there are two forces providing moments, N and F. But N is parallel to the distance to the center. So N doesn't provide, it provides a zero moment. Okay, so the only force that provides a moment now is the frictional force. So if I try to move like this, the friction would cause my person to topple. Right? So I will end up in this situation. Because the frictional force provides an unbalanced moment to my bicycle rider. And that's no good. Because that causes toppling. So if the cyclist remains upright, the unbalanced moment causes him to topple. Okay, so banking must somehow be the solution, but not this time, not the road banking, but the cyclist bending inwards. So let's set the diagram up again. Now the normal force and the weight no longer act directly through the same line of action. They are displaced by a small distance because the tires feel the normal force, but the weight acts through the CG. Right? And the friction also of course acts on the tires. So is this object in translational equilibrium? Still no, right? Because there's a net force in the horizontal direction. But is it in rotational equilibrium? Let's find out. Right, let's find out. So this is the CG. We'll take moments from that point. The normal force, according to this diagram, does it provide a moment? Yeah. It provides a non-zero moment now. And the frictional force provide a moment? Yep. It provides a non-zero moment as well. But they are in opposite directions. The normal force provides an anti-clockwise moment, and the frictional force provides a clockwise moment. So these two must somehow balance. Right? Does he still have a net force in a radial direction? Yeah, he still has friction. So he can still move in circular motion while being at rotational equilibrium. So let's do the mathematics. Let's consider the angle in which the CG makes towards the vertical theta. So I want to find the component of the normal force that is perpendicular to h, so that I can find the moment. So that's going to be nh sine theta. Of course, the component of friction that would give me a perpendicular direction to h, that will give me my anti-clockwise moment. This is the clockwise moment. It will be fh cosine theta. So this equation is anti-clockwise moment equal to clockwise moment using theta that I defined. That's all. But earlier on, I said that the frictional force must be able to be represented in terms of circular motion equations, right? Because the frictional force is the net force. So it is the centripetal force. So I can replace F with mv squared over r. We did that in the first step in part A. Right, so now I'm able to solve for theta. In this question, with the cyclist and his particular speed and weight and all that, the angle he must maintain is 48.9 degrees. It's a very special particular angle which you must maintain so that you are at rotational equilibrium. Now, I'll just end off by saying, this is the physics, it works. Right? But your body doesn't do physics, right? It doesn't have to perform these calculations. But you don't need to know physics for your body to do physics. Your body is naturally able to bend at the angle because if you tilt too much, then the anti-clockwise moment becomes too large. Your body will naturally tilt itself back in order to restore equilibrium, rotational equilibrium. If you are doing insufficient, right, the wheel part will tend to slip forward because the clockwise moment will not be too large. So your body will naturally know how to tilt a little bit more, therefore maintaining the correct angle as you cycle. Very special, it's very amazing, right, that your body knows how to do all this without a single drop of physics. But at the same time, right, our physics confirms our intuition about our bodies. Then about the things that we feel, about the roller coasters. So of course, this is the use of physics. We're able to explain all of this when our physics is correct. Right? So if it happens in reality, physics should be able to explain it. So in addition to producing all the wonderful gadgets that we can, right, using physics, we should also be able to explain every other possible instance of reality using physics. So this is another case where it's easily explained. Right? So now you can account for why you're bent towards the arc as you cycle around it. Okay, the lecture will be available online. I'll send you all the slides as well, so don't worry about whatever you have missed out. Okay, that's the end of this lecture, and we have gravitation to cover before we end the term.